Good morning to everyone. In today's video, we are going to see application of network theorems to electrical networks. The practical application-oriented thing we are going to see through the MATLAB software in this video. Already in your classes, in your regular class, we just solve the numericals of different theorems, superposition theorem, Thevenin's theorem, Norton's theorem. Now we are going to apply those theorems and evaluating. Instead of saying the application, I can say that evaluating your theoretical values with the system output. Okay, so when I'm going to apply the same theorem through the software, whether the software is also getting the same values or not, I'm going to check. Okay, so for this, I'm taking the platform of MATLAB software. Okay, so I'm just going with the MATLAB software. So many of you are aware about this. So how to create its whatever the network, all those things we can see. Okay. So I'm going to share the MATLAB window. So now I'm using the MATLAB 2014B version. Okay. Please have a little bit patience while doing any program through the MATLAB, because it is having the memory of, size of around 20 GB. So that's why it will take a little bit of time to install. Meanwhile, I can say a few words about your Thevenin's theorem, Norton's and superposition theorem. So when I consider any circuit, uh, the circuit current or the current through the any element or voltage across any element can be found out through different ways. Either you can use the nodal analysis or mesh analysis to find out the voltages and currents. But to have a mathematical proof for the theorems, we can go with the different theorems. If you go for the complicated networks, we are going to apply for this theorems. In Thevenin's theorem, we can say, okay, in Thevenin's theorem, we can say whatever the complicated network, it is reduced to three elements. That is, first one is your load, and second one is the source, and third one is the equivalent impedance. So we will see that one in a coming couple of minutes. Okay. So here, this is the MATLAB window. In this MATLAB window, we are going to apply these theorems in Simulink model. Okay, in Simulink model. Here we are having two varieties of files. So first I just go for the new file. If you observe here, we are having the script model of files also, and figures and models. So now we are using the Simulink model, okay, to design our circuit. So I can go for the Simulink model. So if anybody interested to know in detail of the MATLAB, the respective links will be provided in this video description. You can go through that. Okay, then coming back to the Thevenin's theorem, whatever the complicated network is there, it is reduced to three elements. One is the load, which is already provided in your complicated network. The next one is your equivalent voltage source, and third one is the equivalent impedance. And this is your MATLAB Simulink model window. Okay, so whatever you are observing here right now. Okay, so that is so just place. Okay, this is your MATLAB Simulink model window. So when you observe this one, okay, so I just make it here. So here, if you want to open the new file, you can go for the new symbol here. If you want to save or if you want to modify any elements, you can do from this. First of all, to create the model, we require the certain library elements because I can't draw the resistor without any help. So already it should be available in the system. I mean, in the software, it is provided through your library browser. So simply click on that library browser. A set of toolbox because the MATLAB is not um, belonging to electrical or EC, I mean electronics or whatever the signals and systems or whatever the mechanical candidates. So it is having its application in different fields of engineering. So here we are going to see these different toolboxes, what are the commonly used blocks, all those things in detail in our previous videos. Now, my interest is I want to design a circuit. I want to design a circuit and find out what will be the current flowing through that uh, particular element. And I just want to verify the same thing with the Thevenin's theorem. Because I want to verify here, because without knowing what is the actual current flowing through the element, I can't say that this is the current flowing. Okay, so I just want to draw this actual circuit, then I go for the Thevenin's theorem first. Okay, so for this, I am going with the Simscape toolbox. So here, if you click on this, you are having different varieties when you go for the hydraulics model or mechanical model or power systems or different types of utilities. But we are going with power systems. In that, specialized technologies. If you observe here, we are having different sources, elements, and interfacing elements, machines, and measurement units, and power electronic devices. Among all those, I'm just first place the power GI block. Okay, so you can understand how to place the elements also. The first model is I just simply drag and drop the element, and the second model is also there. I just place. So for the circuit, the most important element is your source. I'm going with electrical sources. In this, I'm going for the DC voltage source. For this, simply right click on it and add the block to the model untitled because the title of your model is untitled. Okay, so that's why it will displaying as a untitled. If you rename with this, any other name, you can. So after getting that element on your window, you can place wherever you require. Okay, so next I just go back for the specialized technologies. Now in the circuit, I want to place a T network. So for this, I'm going with the elements. Here you can observe this different types of elements from the breakers to the ground. Okay, what are the neutral points or resistors, all those things will be available. Please make sure that we are having two varieties. If you observe here, we are having series RLC branch as well as series RLC load. Okay, if you go with the RLC branch, they're asking you what is the resistor value, inductor, and capacitor values. In the same case, if you go for the load is the element where it consumes the active and reactive powers. So it is asking the values in terms of active and reactive powers. Okay, so I know only the resistor or inductor or capacitor values. That's why I'm just choosing the series RLC branch. So please make sure that which element you are choosing, what are the parameters you supposed to incorporate there. Okay, so I just need a resistor. So double click on it and drop the box and choose the resistor. So if you want to give the resistor value by your own, please give the whatever the resistor values you want to provide. Okay. So when you observe this, it is somewhat little bit lengthy. Okay. If you want to rename this thing, you can simply rename. Okay. So I just want to give it as 50 voltage source. So 50 volts or 50 V is more than enough. So simply double click on it and provide whatever the value you want to give. Okay, similar fashion, you may give the value of the resistor. Okay, you may give the value of the resistor, or you can simply give it as an R1, R2. So double click on it. And so if you want to have the similar element of different value, please right click on it and drag this. Okay, drag this. Okay, even for line connection also, if you connected in straight line, automatically a line will try to appear. So you can simply click on it. Okay, so, and when I'm double click, I just want to change the value from 82 to 47. Okay, so I want to change this name also 47, and I require one more two resistors. Okay, anyhow, no issue. So right click on it, rotate the element. And similar fashion here also, right click on it, rotate the element. Otherwise, you can simply copy it, no issue. So I just change the value here as 150 volts, 150 ohms. This one has 150 ohms. And this value as 100 ohms. With this, I can say that I completed the whatever the circuit. So if I join that right hand side, the circuit is closed circuit. But in this circuit, I'm interested to know what is the current flowing through the 100 ohms resistor. So to know the current through any element, the measurement quantity, I mean the measurement meter is your ammeter. So from this, I go for specialized technologies again, and I choose the ammeter here. Okay, I choose the ammeter. So I can choose the ammeter and connect it in series with the line. So I can rename here also, because the circuit should be in perfect for looking. You may ask the question, is it compulsory to rename the every element? No, no need. But the only thing is, whatever the names are there, it is difficult to identify. Okay, if you're not rechanging, and it is not that much of looking wise, it is not that much of good if you write the entire name also. So here I can measure the current here, but I can't able to know whether what is the value, because the display is not available right now here. So you can go for the display unit from your commonly used blocks. So better I know where the voltage is available, where the resistor is available, all the things I know. That's why I can simply go for the toolbox and directly I can search. If you don't know like that, you can simply type the required element, okay, required element on your search box, and then you can able to find out which element you require. But the only condition I can say here, you have to give the name of the element correctly. Without giving the correct name, because I know the resistor I required, but actually the resistor is not with the name of directly. It is in the name of series RLC branch. You have to provide series RLC branch to know that resistor. Otherwise, the whatever the remaining resistors from where you may go for the other toolboxes. In the other toolboxes, there may be another resistors. Those will be displayed, but the actual resistor will not be displayed. So you must be have little bit care while searching the elements. So here, when you type on the search box, it searches all the toolboxes and gives the all the results belonging to this such item. So this is your element. So choose and display, add it to your window. So this is where I'm going to connect. Okay. So your whatever the runtime is there, it is only the display blocks. There is no issue. If anybody having any doubt, what is the current flow in here, you can go for the theoretical calculations, or you may check the theoretical calculations window, video in our channel. Okay, how to calculate a current through the element, all those things is already available. So whenever you click on it, okay, whenever you click on it, you can able to observe, okay, you can able to observe what is the current flown through your 100 ohms resistor. Okay. Now I want to convert this into an Thevenin's equivalent circuit. So in Thevenin's equivalent circuit, already I know that the load resistance is 100 ohms because the current flowing through the element is nothing but your 100 ohms. So it is having the 100 ohms, 100 ohms in the circuit. Then what are the rest of the elements? What is the equivalent voltage and what is the equivalent impedance? So now try to calculate what is the equivalent voltage first. Okay. So for calculating the equivalent voltage, what is the procedure we need to follow? What is the procedure we need to follow? We can simply remove our load voltage, load element. There we are going to supposed to measure the voltage. So simply I just drag in the rest of elements. Okay. So maybe it is not suggestible to copy paste, but to avoid the unnecessary whatever called time delay, I just copied the element. I just removed the whatever the load resistor there. There I just simply place the voltage measurement unit. So here across the load, I'm going to measure what is the voltage available. Okay, what is the voltage available? So simply I'm placing this. So if you are not connected properly, it is displaying as what are called dotted red lines. So that is the one of the indication your connectivity is not the correct. Okay. So this is 82 and okay, already is 82 is available. That's why it is warning. So I can rename it as 82 O. O is nothing but your ohms. So that's why I can give this. 82 ohm, and this one is your 47 ohm, and when coming to this, it is 150 ohm. Okay, so now we're supposed to find out what will be the voltage across your load. Okay, what is the voltage across your load for same application of voltage? So the applied voltage is 15, but the across your load around 9.698 volts is appearing. Okay, so this is your VTH. Now we're supposed to find out what is your ZTH. Okay, what is your ZTH? So don't think wrongly. I'm simply copying things. Okay, so I'm just placing. Okay, okay, very good. Now it is coming with name itself. So for calculating the Thevenin's impedance, the condition is we have to reduce the, okay, we have to reduce the source. I mean, whatever the input, if you're having the voltage source as the input, we have to short circuit. If you're having the current source, we have to make it as an open circuit. So apply the same thing, remove the source and place the whatever called meter. Okay, whatever the meter you require. So we require the input impedance measurement unit. Okay. Okay, now, so done. We connected this Z impedance. You may ask the question, for the voltmeter and ammeter, you provided a display unit, but what about your impedance measurement unit? Okay, so please observe here. So already we are having this power GA block. Now you can understand what is the use of it. So again, run the element. So there is no display block to display what is the equivalent impedance. Please go to your power GA box. In power GA box, go for the impedance versus frequency measurement. Okay, impedance versus frequency measurement unit. There you can able to observe. Okay, so it is computing by itself and it is displaying that the impedance. Okay, the impedance value, the Z value is 100 ohms and the phase difference is 0 degrees. So when I say that the phase difference is 0, can I go for the resistor? Okay. So can I say that this is the resistance? So the Z impedance is nothing but 100 ohms. For example, if it is become 90 degrees, I can say that it is an inductor. Okay, if it is in 90 degrees, I can say that either an inductor or capacitor based upon the lagging, I mean, plus 90 or minus 90. Okay, so fine. So here I can able to get what is the VTH and what is the ZTH here. So now try to draw the same circuit here with different values. So I can go for the same circuit. Okay. I just modify the values, but okay. So I just modify this values. So what is your VTH? It is around 9.698. Okay. The value of resistor is 9.698 volts. Listen. 9.698 volts. And what is your Z impedance? The Z impedance value is 100. Similarly, your load resistance value is also 100. So already 100 ohms is existing. That's why it is warning. Already it is existing. So that's, can I change with 100? Oh. And the next one is 100 oh 1. So I just modify this value 100. And this is already, it will be 100. So no issue. So I can run this same circuit. Okay. So the way I need to represent this is the actual circuit. Okay, this is the actual circuit. I'm changing this circuit into to find the VTH, that is Thevenin's equivalent voltage. And from this main circuit, I just want to find out what will be the Thevenin's equivalent impedance. By knowing these two values, I'm just replacing the circuit in such a way that the circuit consisting of only voltage source, which is in series with the Thevenin's equivalent impedance connected across whatever the required branch you need to find out the voltage or current. So this is your load impedance. I didn't modify anything on your load impedance. Whatever the branch is there, the complete branch, I just keep it as is. So now you can say this, whatever the current you got through this software for actual circuit and for Thevenin's circuit, it is same. The Thevenin's theorem is valid or it is evaluated in this MATLAB software. Similarly, you can do for the n number of circuits with n number of parameters. For n number of parameters. For this, I just conclude for the Thevenin's theorem. Thank you.